Hey, Harsh here. If you have ever sat through a system design interview, you have heard the golden rule of distributed systems, the CAP theorem. You are told to have three choices: consistency, availability, and partition tolerance, and you can pick only two. It's a cheap, fast, and good of the computing. But here's the $1,000,000 question: what happens when your internet isn't broken? The CAP theorem is silent on this. It doesn't tell you how your database behaves during the 99.9% of the time when everything is working perfectly. Today we are going to dismantle the pick 2 myth. We are going deep into the PACELC theorem, the framework that actually runs modern tech stacks like DynamoDB, Cassandra, and TIDB. By the end of this video, you will understand the trade-offs that keep the internet running. Let's start with the basics that trip people up. The CAP theorem says you can't satisfy all three properties simultaneously. But beginners often think this means they have three equal options: CP, AP, or CA. In a distributed system, you cannot choose to ignore partition tolerance. Network failures are inevitable. Cables get cut, switches fail, and packets get dropped. If you choose CA, ignoring partitions, you aren't building a distributed system, you're building a monolith. If a partition happens in a CA system, the system effectively fails completely because you can't tolerate the communication break. So the real choice isn't pick 2, it is when the network breaks, which is partition tolerance, do you want to be consistent or available? We need to be precise here. When we talk about consistency in CAP, we aren't talking about C in asset transactions. Asset consistency is about integrity constraints, like ensuring you can't transfer money you don't have. CAP consistency is stricter. It's essentially atomic consistency for linearizability. It means that if I write data to node A and you immediately read from node B, you must see my write. All nodes must see the same data at the same time. Availability is also tricky. It doesn't mean the correct data is available. It means a response is available. If a server is up, it must answer you, even if it hands you the data that is 5 seconds old. Think of it like this. You're designing an ATM network. The cable between the ATM and the bank HQ is cut. A customer tries to withdraw 100 rupees. If you are a CP system, consistent, the ATM says service unavailable. It refuses to guess your balance because getting it wrong means giving away free money. Now imagine you're designing a shopping cart for Amazon. The network glitches. Do you stop the customer from adding an item? No, you let them add it. You prioritize availability. AP. Maybe the inventory count is slightly off for a second, but you never block the sale. In a CP system, we must sacrifice availability to ensure we never serve bad data. In an AP system, we accept that the data might be temporarily inconsistent to ensure the system never goes down. CAP helps us handle failures, but network partitions are rare. Maybe your system is partitioned 1% of the time. What is happening for the other 99% of the time? CAP tells you nothing about performance during normal operations. If I design a database that takes 30 days to return a query, it is technically available according to CAP, but it is useless to the user. It is a massive oversight. We need a framework that helps us balance trade-offs when the system isn't actually working. That framework is PACELC. PACELC stands for if partitioned, choose availability or consistency, else, meaning normal operations, choose latency or consistency. This changes everything. Even when your network is perfect, you still have to make a choice. If you want strong consistency, everyone sees the same data instantly, you have to pay the price in latency. Why? Because data has to travel to all replicas and get confirmed before the write is successful. If you want low latency, you can have relaxed consistency. You can't have instant global data update and lightning fast responses simultaneously. Let's apply the real tools. Take DynamoDB or Cassandra. These are classic PAEL systems. If a partition hits, then prioritize availability. They keep the app running. But what about the else? When the network is fine, they prioritize latency, the default to eventual consistency. They give you the data fast even if it hasn't replicated to every single node yet. This is why these databases are favorite for high traffic apps like e-commerce or social media, where speed is user attention and being slightly out of sync is acceptable. On the flip side, we have PCEC systems like Google's Bigtable, HBase, or VoltDB. If a partition hits, they choose consistency. They will block your request rather than risk data corruption. But look at the else. Even when the network is perfect, they choose consistency. over latency. This forces the system to synchronize before confirming a write. This makes them slower, but it guarantees that if you read a record, it's 100% accurate. This is the architecture you want for billing systems or inventory management, where overselling is a disaster. You always aren't stuck with a hard-coded decision. Many modern databases offer tunable consistency. Azure's Cosmos DB has 5 different consistency levels. Cassandra lets you decide per query if you want to wait for one node or all nodes. Look at TIDB or CockroachDB. They use raft consensus algorithms that we had in the last video. They are technically CPEC systems prioritizing consistency, but they are engineered to recover so fast that they feel highly available. They blur the lines, giving you strong consistency without the massive downtime penalties of older CP systems. So how do you choose this in your job or your next interview? First, stop saying I will pick availability and consistency. You can't. P is mandatory. Second, ask about the else. Ask, when the system is healthy, are we okay with higher latency to ensure data accuracy? If you're building a billing app, you want PCEC. You pay the latency tax for accuracy. If you are building a real-time game leaderboard, you want PAEL. You want speed, and if the score updates 500 milliseconds late, nobody dies. Cap theorem is a great starting point, but PACELC is the map for real world. Remember, you can't have everything. You have to choose your battles, either against data corruption or against latency. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.